Okay, so I wanted to do a couple of practice problems out of the section 4.8 packet so you guys could refer to them. So this is the limiting reactant practice problem number 3. It's on page 249 of section 4.8. And let's go ahead and start by marking this up. So this problem says when ammonia is passed over hot calcium, calcium hydride and nitrogen gas are formed. What mass of calcium hydride results when 20 liters of ammonia measured at STP, 150 grams calcium are reacted? What quantity of excess reactant remains? So first we need an equation. So we are reacting ammonia and hot calcium. So ammonia is NH3. Hot calcium is just calcium metal, Ca, and it tells us that calcium hydride and nitrogen gas are formed. The easy one there is nitrogen gas. Nitrogen by itself is diatomic, N2, and calcium hydride. Well, calcium is a +2 charge. It's going to form with hydrogen there, so hydrogen's going to take a -1 when it does that, and that formula is going to be CaH2. So to balance this, I notice I've got 2 hydrogen, 3 hydrogen, so I'm going to need to double that. Put a 3 in front of the calcium hydride. That gives me a balanced number of nitrogens, but I do need to balance out that calcium with 3. So now I have a balanced equation. And it says what mass of calcium hydride results when 20 liters of ammonia, so this is my first given, is measured at STP, my magic letters there, and 150 grams of calcium. So I've got 2 reactants. 2 reactants set up 2 problems. So let's do this first one right here, the 20 liters of ammonia. So 20, there we go, 0.0, that's ugly, but that's fine. 20.0 liters of ammonia, NH3. If it's at STP, then I can use my 22.4 liters of NH3 to 1 mole of NH3. So I'm now in moles of NH3. It specifically asked me for calcium hydride. So I need the mole ratio between ammonia and calcium hydride. So ammonia is in the numerator here, so it needs to go in the denominator here. 2 moles NH3 with the new numerator being 3 moles calcium hydride. Okay, and then it says what mass, so I have to take this one step further and take it to grams. It's a definition, 1 mole of calcium hydride, and I need the molar mass of calcium hydride. Calcium is 40.08. 2 hydrogens would be 2.02, so that would give me a lovely round number of 43.00 grams of calcium hydride. Okay, so my liters NH3 cancels, moles NH3 cancels, moles calcium hydride cancels, leaving me with grams of calcium hydride. So I started off with 3 significant figures, so I'm going to write out my mass to 3 significant figures, punch all that in the calculator, and I would get 57.7 grams of calcium hydride. So that's only the one thing. So I've done that one. Now I need to see how much calcium, how much of the calcium hydride that calcium would produce. So I start with a whole another problem. So 150.0, not 0.0, just 150 grams calcium. Convert that to moles using the molar mass of calcium, 40.08 grams calcium to 1 mole of calcium. And now I need the mole ratio between calcium and calcium hydride, which is a lovely 3 to 3, which makes sense. 3 moles of calcium, 3 moles calcium hydride. And the exact same thing at the end of my problem because I need mass of calcium hydride. So I'm just going to rewrite what I did directly above. 43.00 grams calcium hydride. Okay, my grams calcium cancels, my moles calcium cancels, my moles calcium hydride cancels, leaving me with grams calcium hydride. 150 divided by 40.08 times 3 divided by 3 times 43, and that is going to give me a mass to two significant figures of 160 grams of calcium hydride. So the question asks, what mass of calcium hydride results? Well, it's the smaller amount. So this is the mass that results, because I'm always going to make the smaller of my two. So I would say that the NH3 is limiting, that this 57.7 grams is my theoretical yield. And then the second part of the question says, what quantity of excess reactant remains? Well, the excess is calcium. So that question is asking me, if I start off and use all 20 liters of ammonia, how much of the calcium do I use? That's a third problem. We start again with the limiting reactant, 20.0 liters NH3. I will do the exact same initial problem here, 22.4 liters NH3 to 1 mole NH3. But now instead of switching to calcium hydride, 2 moles NH3, I need to switch to calcium because I need to know how much calcium is required to react with my ammonia. So that's this 3 moles here, and I'm just getting that from this 2 to 3 ratio up in the equation. And I was given grams here, so I have to take this to grams. So in 1 mole of calcium, I have 40.08 grams of calcium. Multiply all that together. I'm going to write that to 3 significant figures, and at 3 significant figures I have 53.7 grams of calcium used. That is how much calcium I used to react with all 20 liters of my limiting reactant. So how much remains? Well, I started with 150. I subtracted off 53.7, and what remains is going to be 96 grams of calcium remains. Okay, so that's how you do that problem. Again, the first step in any of these problems, take both of your givens, take them all the way to whatever product is indicated. Figure out what's limiting. The limiting thing is whichever thing gave you less product. The theoretical yield is that smaller amount of product, and then you can figure out the remaining of the excess by taking your limiting, converting it to the other reactant, the excess reactant, and then doing this subtraction. So that's that problem. The other problem I wanted to do for you is problem number 2 in the percent yield problems. All right, so problem number 2 in the percent yield, that is on page 252. And it says a solution containing 15.2 grams of barium bromide is, barium bromide, technical difficulties, here we go. There we go. Barium bromide is reacted with a solution containing excess. Isn't that nice? Excess, that's extra, so I don't have to do the full limiting reactant problem here. Sodium phosphate to form 9.5 grams of precipitate. They don't tell me what precipitate that is, but they ask for the percent yield of the reaction. Begin with the balanced equation. So barium bromide. Barium is a +2, it's in group 2. Bromide is bromine, it's a -1. So I start off with BaBr2. Solution. Sodium is in group 1, it's +1. Phosphate. Fate. That is a polyatomic. It's got a -3 charge. Cross my charges in a 3PO4, and that's the solution. That is a double replacement reaction. So I'm going to switch up the barium and the sodium. Sodium is a +1. Bromine is a -1, so those fit together with a Na Br. Sodium never, ever, ever makes solids, so that's aqueous. And then my other thing is a barium with a +2 and the phosphate of -3. So not Na, Ba takes a 3 and phosphate takes a 2. And since this was in solution, this must be my solid precipitate. So Ba3PO4 in parentheses with a 2. So that's my balanced equation. I have started with that. Good job. And I've got this much barium bromide. How much precipitate do I make? Okay, well, we've got to balance it now, so we are not there yet. I need a 2 in front of there. I need a 3 in front of there. That's easy from that 3 and 2, and that's going to give me a 6 over there. So start with the barium bromide. 15.2 grams BaBr2. Only thing you can do with grams, take it to moles. The molar mass of barium bromide, barium and bromine are actually both quite heavy elements, 297.13 grams barium bromide to 1 mole barium bromide. Now, I need to take it to the precipitate, which we identified as this thing. So that ratio is 3 moles barium bromide in my denominator and 1 mole of the barium phosphate, Ba3, PO4, 2. And then lastly, I need grams because my percent yield is going to have to deal with this number, and that's in grams. So 1 mole, Ba3, PO4, 2. That is an even larger molar mass, 601.93 grams. Figure all of that out. We've got 3 significant figures here, and that's actually not as large as you might think. It comes out to 10.3 grams of the barium phosphate. Okay, so this 10.3 grams, that is my theoretical yield. That's how much my calculation says I should make. This amount is my actual yield. That's how much it says I actually made. So percent yield is simply actual over theoretical, multiply it by 100 to move your decimal. So if we do that, my actual was 9.5. My theoretical is 10.3. Divide those two in my calculator, move my decimal over twice with the 100, and I would have 2 significant figures here because of the 9.5, and that's going to give me 92% yield. Not bad, 92% yield. We'd be rather happy with that. Okay, so that again is the third practice problem for limiting reactants and the second practice problem for percentage yield. And hopefully that will help you with both your homework and getting ready to study for our quiz on Tuesday.